Everyone, thanks for making it again. So glad you can make it. And again, my apologies for last week and this week. I made a mistake. I had scheduled it, but I didn't enter your email, so that's why you didn't know about it. So I'm truly sorry for that. I hope those who were not able to attend last week or because maybe you knew too late or something, if you had chance to go through the video on Ulan X, what we covered last week was the focus was actually defining the specifications of a digital system, where my emphasis really was that you basically have to define what is the behavior of the digital circuit that you're expecting. I repeat that you have to define what is the behavior of the digital circuit you're expecting. You have to specify what are the actual input signals, how many they are, what is their identity. You have to specify what is the meaning or the encoding of a logic 1, logic 0. All of this has meaning. You have to give the meaning, right? And you have to specify how many outputs and what is the relationship between a particular sequence of inputs. What would be the particular sequence of output corresponding to that sequence of inputs, and you have to do this completely for all possible cases that the digital circuit can see. And let me reiterate, this is not design. We are not starting the design yet. This is just specification. You're stating in as much detail as possible what the design will do. You are specifying what the design will do. And the reason I need to emphasize this over and over again is because from the past students, I've noticed a trend. Most people, when they just fresh from undergraduate, they've not done enough of digital design, they rush to the process of designing without actually detailing out or actually describing what is it they're going to design. So then they run into trouble and they think that this trouble is actually, oh, it's very difficult to design digital circuits. No, it's not. You can't design a digital circuit when you have not defined what it's going to do. So the first step is always you need to define what it's going to do. And last week we had this example of designing a safety lock system, implementing a passcode where you have to enter a 4-digit sequence and went through. There are numerous ways you can input the data, and then we talked about sequences, all possible types of sequences as far as we could. What is permissible, what is the behavior of every type of sequence that we can think of. And then we ended up saying that we have to really specify. We started by specifying in words and with diagram. That's okay. This is not a state machine. This is just a diagram specifying what will be the behavior. And then ultimately, we went to saying that the complete specification will be when you actually have timing diagrams showing the actual ones and zeros that could happen, and what would be the ones and zeros, sequence of ones and zeros in the inputs. In this case, is the key, and the sequence of ones and zeros in response to that input at the output. Okay, so that's where we sort of stopped. And today I'm going to go 2 steps further. Okay, and there was this set of steps that I generally say. The first thing you need to do is you need to specify what the system will do. Again, this is not design yet. This is just saying in as much detail as possible. And you're doing some heavy thinking here. And you are also making some choices in a way. You're trying to state how many input signals there are, how many output signals there are, what do the values of logic 1 and logic 0 mean for the input and output, what are the acceptable input sequences, and what is the response, what is the output sequence that the circuit must generate in response to that input sequence. And you have to do this for every possible input sequence. Okay. Of course, you're not going to be able to draw these timing diagram for every possible input signal sequence, but you have to find a way to generalize it. Let's say, okay, these are the things that have to be done. Okay. Now, the next step today, if you are all clear on that part on specification, is great. You can ask me a question now if you have any doubts about that specification part. If you have any doubts, just raise your hand or turn on the mic or type something. I'm happy to answer questions on that. So I'll just wait for about a minute or so. Okay, looks like everybody has no questions. So if that's clear, then today we go to the second step. That is, once you have defined the specification of your design, you have to start thinking about how are you going to test? How are you going to verify that whatever you design is working? Okay, let me repeat. We've not started design yet. Your circuit is going to be this black box. All you've done is you've specified how many inputs, how many outputs, what are the patterns of bits of the inputs that can be accepted, and what is the response of your output to that patterns. Now, once you define that specification, you have to come up with a sequence of patterns where you will use that to check, does your circuit as you designed it, does it do what it's supposed to do? So you've defined the you've defined the specification. Now you have to define what type of tests you're going to run to verify that the circuit has implemented the logic correctly, that it's actually implementing the specification. And you would be right if you ask me, well, if I specify, isn't that already saying the test? Yeah, in a way it is, but you can't test every possible sequence in the input. Just like how when you do a specification, you won't be able to draw every single timing diagram for every single combination. Maybe for this small case, it's possible, but I think if you've gone through the video or if you've followed me with the discussion last week, you see that, you know, as we start adding all possible combinations, that there's just so many sequences that can happen, right? So the idea now is for you, after you've specified the specification, okay, you also should define what are the test cases you're going to test, right, for this particular circuit, just to verify that it's working. Okay, so I'm going to pick off there and just use this as an example. So we're talking about this passcode system again, and we're saying that 4 digits will open a lock when the user enters 5606. Okay, and you're going to have to press the confirm button after 5606, and if there's only 4 sequences, it's going to unlock, and if there is more than 4, it's going to remain locked. If there's less than 4, it's going to remain locked, and if there are 5 incorrect tries, the system will not be able to unlock things anymore. Okay. All right, that's what we're going to do. So what do you think are the cases where we have to test our digital system here? Maybe anybody can hazard a guess. What sort of conditions should we put into our digital circuit once we design it, just to check whether it's done what we said it would do, right? And what we said it would do is specification. Anybody want to give a guess?
Test with the correct combination.
Exactly, great. So the first thing you want to test is, of course, you want to test that I'm going to input 5606, press the confirm. I need to see the output become unlocked after 5606 and confirm. Correct. So there is one particular use case you have to test that is correct. Okay, so you can go ahead and specify one of your test case. Okay, you will write down. You can write in any way, but maybe one way would be you can put a table. Okay, you can put a table. Maybe you can say test description. Description of input sequence. Description of expected output. First thing is you test unlock with correct sequence. Okay, this is one test case. Okay, so description of input signal sequence. You can put it in words, or a better way would be you just draw the timing diagram. What is the timing diagram at the inputs you want to do? So for example, here we were using the one hot encoding here for that. So it could actually be you put 5 here, then you put 6, then you put 0, then you put 6 at every clock edge. Okay, so you can actually describe this. Maybe we will have our clock. So I'm starting to actually have the using this as a replacement for drawing that clock signal, because it's just easier to draw, and it gives you the idea that it's actually the clock edges lah. Test this out. My clock edges. So I could say 5606 confirm. Can have can write okay, I think to be faster, I'll just do something like this lah. Key 0, so it's 0, 0, 0, 0. So I said this is on, let's say I said on neck edge, okay? This is on, make a note, flip flop is on neck edge clock. I define my design. 0, 1, 1. 6. 1. 5, 6, 0, 0, 1, 0, 0. 5, 6, 0. Then you can have key 10. This is the confirm key lah. Okay. With this input sequence, this is actually giving the 5606 sequence. The buttons are coming in at every clock edge, and you can describe the expected output. Again, you can take the clock signal here. You can define the output. So we only have one. The output is called unlock, right? It's going to be 0, 0, 0. So it's 5, 6. 6 confirm. We say is maybe opens for a long time lah. Okay, right? Okay, so this will be an example of you define the test case, you define the input sequence, and you define the expected output lah. Here I'm taking a shortcut. I'm trying to save some time because I take too long to draw with my mouse lah. So I just put 0, 0s and all that. But you can actually draw this as a timing diagram, or the better one would be you go to EDA Playground. Okay, and you just write the test bench code to actually put the signals, right? What do I mean by test bench code? I think if you see, for example, the test bench, the examples I give you in the Ulen X, the test bench, you can actually set, like here, you're setting the signal at a particular value. So you can actually use this to draw the timing diagrams. Right? You use the test bench itself to draw the timing diagram. Then you call the simulator, you simulate it, then you'll be able to get the timing diagram. And that's not using this, right? So if you use this is the logic part, you're describing the logic there, then it's actually doing a simulation. But if you use the test bench itself just to draw these curves, it's okay. You can do that. Okay, that's just a quick way to draw the curves rather than writing like that. Now, I ask you the case. Is this the only test case you want to test?
Maybe we want to test with what is the wrong sequence.
Yes, that's right. So that's a good point. So we've tested the correct sequence. Now you have to test.
Doctor, before that, can you explain again on the key 056, like 000 is 11? Can you explain the part again a bit more?
Okay, can. So this is going back to our inputs. We were saying we have to define what is our inputs and outputs, right?
Okay.
So we were saying that one way to do it, you have 10 keys lah, 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is 10 keys lah, 9 here and 1 here lah. And then you have an 11 key, it's a confirm lah, right? Because that is after you press the buttons, the numbers, you have the confirm key to say this is my pin lah. Okay, so that's what we define as our inputs last week. Okay, so one way you can encode this is you can say every key is 1 bit. Okay, so I have 11 bits, bit 0 to bit 10. Okay, bit 0 to bit 10 is 11 bits lah. So we are saying that we define that this one hot encoding. If the logic is 0 means the key is not pressed. If the logic is 1 means the key is pressed. Or there's other ways to define it, that is we can actually encode the keys as you know, either a row and column format lah, where we would say this is let's say we say this is 0, 1, let's say we can actually put 3 bits here and we can put 4 bits here, or we can actually encode it as a number. So there are different ways we can encode the button, right? So you have to decide on one. There are multiple ways, but you decide on one. So I've discussed all those, but now I'm just taking the simplest one, which is, I assume there are 11 input signals, 10 input signals plus confirm button. So that's 11. Okay. Why the confirm was late? Because we were discussing how to improve this design, whether it was sufficient. And then I think Lokman has suggested that there needs to be a confirm button so that you can put in arbitrary number of passcode. That means you can use different lengths of passcode. Is that clear?
Yes.
Okay, so what I'm actually just showing you is here, instead of drawing ones and zeros, I just type but at the clock edge. But in reality, it doesn't have to change at the clock edge. You can assume you change anywhere because this is a key. You as a person pressing the key, you're not going to say, okay, I'm going to wait until the positive edge of the clock. Okay, I press the key. You're not going to do that, right? So that's example where we go to this test case for the correct unlock. This is probably not enough for you to test the correct, right? But you're right. Besides testing for the correct sequence, you must test unlock with incorrect sequence, correct? Okay. So what is an incorrect sequence? What do you think?
1010, like some random number.
Okay, very good. So what you're saying is that 1010, there could be some random numbers. Okay, so you can actually put key 1, key 0. I'm being a bit lazy here lah. I'm sorry. I just want to move ahead lah. But then I'm going to ask you: is this incorrect sequence enough to validate that the design is working?
No, we need to put in a few more incorrect sequence.
Okay, how many more?
Maybe like around 5 or 6.
Okay, so I think this is just it, right?
Sorry,
Mukesh. Sorry, Mukesh. Sorry, just trying to recognize the voices.
Yeah.
Okay. Mukesh, you're right. You said 5 to 6 random example keys.
Yeah.
That's okay. Are you going to keep them to be length of 4, or are you going to vary the length? Could I try 5 key sequences, 6 key sequences, 2 key sequences? Because it's key, and then confirm, right?
Yeah.
So how many lengths am I going to try?
Maybe 5 keys.
5 keys. So I have 5 to 6 random examples for how many keys?
Keys means the length of the code.
Oh yes, length of code for length 4 code. Is it 5 to 6 random examples for length 4 code or what?
Yeah, maybe length 4 code. 5 to 6.
Length 5 code. Length 5 code.
Also okay.
Okay, then length 3 code.
3 code also supposed to. But
Length 1 code.
1 code will be very easy.
Are you going to test it?
But yeah, we're supposed to test every possible ways so that
Is it possible for you to test every possible condition?
yeah.
Is it possible for you to test every possible condition?
No, like exhaustive testing, I don't think so.
Yes, and this is where I will try to demonstrate why lah. Okay, so how many possible 4 key patterns are there?
16.
Not 16, you have 10
Sorry,
keys, so 10 times 10 times 10 times 10. So there are 10,000 possible combinations of 4 keys.
right.
Okay, so how many possible combination of 3 keys are there? So there are 1,000 combinations of 3 keys. There are 100,000 possible combinations of 5 keys. You start to get the picture, right?
Yes.
Okay, great. So as a designer, you need to know, this is where we talk about the explosion of the test space lah. And that's why I really want to make a point that you need to sit and think about how this testing works. If you're talking about maybe for this class lah, okay lah, 5 to 6 example is enough. Then you tell me 4 codes, 5 codes, 3 codes. Okay, enough. I understand that lah. But for your particular application in the chip, where you make one mistake, you pretty much can throw away the chip already, right? And one fab run, I don't know how much is a tape, but I think it's few 100,000 to few million, if I'm not mistaken, right? If you tape the chip incorrectly, if you have one bug, you throw away the chip and all the money that goes into it. So then you have to start thinking. Yes.
Yeah, Dr. Rick, sorry to interrupt, Rick.
Sure.
Regarding because this is just a specification, right?
Okay, great. Lukman, is it?
Test it, yeah.
Okay, so this is specification for the verification, right?
Yeah,
Earlier on,
yeah.
this is the verification part, but you're not doing the design yet. You're just saying, how am I going to test the design?
Understood. So meaning that we're going to explore every thing that we're going to consider in the specification. So thinking of like samples, right? When you're saying how many random samples are we going to key in, like Mukesh given the example. So in this particular case, is it possible that we're going to say that we have this 100,000 possibilities, right?
Yeah.
So is it possible that we're going to put another tool like generator, 100,000 generator of, to key in the.
Lukman, you are exactly on track. You're exactly on track. Most people will use a random number generator. Okay, and they would say maybe if it was fast enough to generate all 10,000, and if you care about the design enough, you generate all 10,000, 1,000, and 100,000. You will do all of that, because if it's fast enough, why not, right? If it takes a day and then your cost of your tape is like few 100,000 or a few million, 1 day of simulation is not going to be worth much. You generate all the possible sequences. Okay. Now, when it becomes impossible to generate all possible sequences, and you can actually do this, right? Because you count how many possible permutations of inputs there are, and then you can start to think about it going crazy. I'll give you an example. How many possible permutations are there for a 64-bit adder? I'm adding 2-bit 64-bit numbers. How many possible? So you have 2 to the power of 64 for 1 times 2 to the power of 64. If you want to test every single combination of 64-bit numbers that can work in a 2-bit adder, a 64-bit adder, you're actually looking at 2 to the power 128 combinations. You can calculate how many numbers there is. At some point, you will run out of numbers. It will be more than the number of stars in the universe. Okay, so that's just to tell you how crazy this is. That's why people don't do exhaustive testing. Right, but I want you to understand this so that you know that if the number of combinations is small, you pretty much should just take the practice to test all of them. If it's big, you want to actually kind of randomly choose, but you want to choose a decently large enough number. Frankly speaking, 5 to 6 combination a bit small. But what I want you to recognize in this case is not just you have the combinations of 4 input length. You need to test different input length combinations, okay? Some shorter, some longer. As long as you recognize that, is good, right? Because then the other question is just how much time, how much money, how much resources you have to do all the tests. And we're actually not done here. Here you're assuming the keys are being pressed one after another at the clock cycle. You've not tested the case where you press one key and then you wait for a certain number of clock cycles, then you press another key, then you wait for another different number of clock cycles, right? You could have one key, then you wait for 1,000,000 clock cycles, right? Because your clock is running at maybe 1 gigahertz or something, or maybe it's 1 megahertz. You press one key, you wait for 1,000,000 sample clock cycles, then you press another key, wait for 1,010,000 cycles, because there is a difference, right? Human beings don't press keys so fast. They're not machines, right? So there's going to probably be a gap of time in between. So that's also something, if you start looking at that, the number of combinations explode lah, because you can actually say one key followed by 1,000,000 clock cycles, one key followed by 1,000,001 clock cycles, one key followed by 1,000,002 clock cycles. You test all these cases, right? So in that case, it's more likely I want you to identify what are all the possible ways this could change, and then you just take a few representative samples in each case for this class. Now, in the workplace environment, as long as you can identify these, later on you can add more and more samples, random samples, and increase the number of samples lah. Okay, is that helpful? Do you understand what I'm trying to say?
Yes, Doctor.
Okay, thank you. Okay, and here why I put the test case is because the output is fairly straightforward. It will always be the same for all of them. It has to be unlocked, everything 0, right? So this is why it's kind of nice to be able to group test cases lah. So this is how you can specify specification. Okay, the earlier one where you kind of identify certain patterns and then what is the behavior. And this is how you're going to do the testing. Okay. Now, have we covered all the possible cases that you want to cover here? What other test cases do you think we're missing, or this is good enough?
You mentioned about the one hot. So what if 2 or 3 buttons are pressed together?
Ah, great. You've been paying attention. Good. Right. So you also have another test case. So I would argue these two test cases are when everything is functioning perfectly lah. When you have got a very good user pressing one button at a time, trying to behave properly lah. Then tests unlock with multiple buttons pressed together. Okay. This is the case where, again, you might do something crazy like this, right? And again, you can start to count how many possible cases there are where I can press 2 buttons together, 3 buttons together, 4 buttons together, 5 buttons together, so I have maybe 10 buttons, but it's possible that for the first key, I actually press 2 buttons, second key, I press 1 button, the third code, I press 3 buttons. There's just so many permutations, right? But like I said, all I need you to recognize is maybe you can say I randomize the number of buttons that are pressed in each key, but it needs to be more than one lah, because the single button case you've covered in these two cases. This is the many button case. And what are you actually looking for? You're actually looking for the case where if there's 2 buttons pressed, it doesn't actually unlock, right? Because again, if you look like this, there is going to be a possibility where the user just press all 10 buttons and then just press 10 buttons, 10 buttons, 10 buttons, 10 buttons, and then suddenly the thing unlocked, because your logic seems to be implementing. I just look, as long as key 5 is pressed, I say okay. As long as key 6 is pressed, I say okay. But actually, I don't know which key I press all 10 keys, right? So this test case is to test that you are not having the error lah. Okay? Can, okay. Is there any other test case that you should be looking out for?
If the design already unlocked previously, then without new inputs, they press confirm.
Okay, unlocked design without new inputs, press confirm. Okay, so here now we start to come across a funny situation, because we've discussed up to unlock, but we actually haven't discussed the behavior, what happens after you unlock, right? So now you start to realize, oh, great, my specification is not complete. I haven't actually discussed what happens after the unlock, right? So you already press this sequence of 4 passcodes, you press confirm, it's unlocked. Then what? Does it stay unlocked forever? What do you all think? How are we going to add the specifications? Yeah.
After it unlocks, then there's a certain amount of time it will reset back until you lock.
Okay, that's a good point. You can have a timer function where after a certain amount of times it sets back to lock, but is that enough? After n minutes, unlock goes to lock. Is that enough? What happens if the door is open and then it just suddenly goes to lock, but you know the thing is open, right?
Yeah, like maybe it's like additional features we can add is like, let's say it's a door lock. If the door doesn't close on that time, an alarm should ring like saying that we have to close the door. Not the alarm will keep ringing. So when it closes the door, it locks.
Okay, so how do you know when you close the door?
Yeah, that's another input where it senses the door.
Exactly. So you can put in another sensor lah.
Yeah.
Another sensor. Okay. So great. So as you can see, the back and forth between specification and verification is really useful because it helps you to think very, very carefully about what your design should do. And then you start picking up all the holes and things that, you know, are insufficient, and you start building the case for that. You just have to be a bit careful that you don't end up, you know, every kind of thing you miss, you just keep adding signals, because signals are expensive. You need to know signals are expensive. You cannot just arbitrarily add so many signals, right? You pay a cost for it. And as they always say, the number of transistors to the chip, that's really cheap. So you can add 100 or 1,000 more gates, is not going to matter that much, right? But when you add one more pin, that's a big deal, right? So number of pins is very important. That's why people like to do serial buses and all that kind of stuff, because they're trying to actually reduce the pin count. So you're right, unlock design without new inputs, press confirm. But there's also something that we've not tested. We've not tested the number of incorrect tries. Okay, we have not tested the timer function, right? And we have not actually tested, you see, there's an incorrect tries after reset, and then the timer function after the error, the five errors, we said that it would reset after 30 minutes, right? So there's the reset after you close the door, and there's the reset after incorrect tries. So you get the point. You need to list all these test cases down. You understand what I'm saying?
Yeah.
Okay, great. So I won't belabor the point. I've just said this is how you have to do it. And at this point, you will have a complete design specification. Okay, input, output, what is the, whatever inputs you have specified the output, you know what is the number of input signals, the sensors, the keys, everything, and you know the number of output signals, and you have defined what the logic and one and 0 says. And beyond the specification, you would have specified what type of input patterns and you're going to test and what would be the expected output pattern, right? Because you then would actually just take this whole thing and you use this thing to write your test bench. That's how you would do it, okay? So when you do it this way, you don't actually have to worry lah, like, because then your digital circuit implementation is different. You're separating the specification and the test from the circuit implementation, so you're not going to be too influenced by that lah. And this is important because once you actually start doing the circuit design, most people have too many things in their head and then they forget lah. So these are two very important key steps you need to do before you start any design. You're not even starting the design, but you're just talking about what is the specification and how are you going to test it. So in actual fact, you can actually write the test bench before you even create the design. You follow me with that? Okay, now for some of you, there is an advanced version of test bench writing called assertions. Okay, so with assertions, you can basically ask the tool to check, is there any condition where any other key than this is not unlocked. So you here, this is pretty primitive, where you actually have to specify all the types of combinations, you have to think it through. But the more advanced feature in system Verilog, which I hope you'll be covering under the systems verification class lah. I think some of you have taken it already. You write an assertion, and assertion is basically a command to the simulator tool to check whether the logic will obey certain patterns, right? It's basically a shortcut way of writing a certain kind of possible patterns and asking the tool to check all of it. And if there is one pattern that doesn't obey a certain thing, the simulator will just flag it, right? So it's not even saying it's going to actually. So the way the assertions usually are checked is I think it's part of a formal testing methodology lah. So they won't actually test each and every condition, but they will use combinatorial mathematics. They will actually find some kind of equivalent combinatorial representation, and then they will see that, okay, this circuit actually will fail this condition. So your assertion is actually like a mathematical constraint, and your circuit design is actually a mathematical equation. And that's how it checks the assertion. So it's able to check multiple patterns without running the individual patterns. I hope I'm making sense here. Let me know if I'm not. So what I'm sharing with you here in doing the test specification, I'm sharing a relatively old and primitive method where I want you to specify every single condition lah. The reason is because I want to walk you through the process where you actually think as a designer, what are all the possible use cases there are, right? But this is fairly primitive because you have to specify the exact bit pattern. And the way you check is you put in one bit pattern, you look at the output pattern, and then you check the output pattern at every time is correct. Then you say, okay, for test case 1 is correct. Then test case 2 is correct. Then you have to do for a whole bunch of test case. Nowadays, there's a more powerful way to do it, which is writing assertions, which is rather than saying the actual binary pattern and simulating the actual binary pattern, you describe the pattern as a pattern lah. There's a certain way you can write the assertions where you talk about how many up and down numbers and all that kind of stuff. And the simulator will check this, but it will not check it in the way where it actually simulates one pattern and then check the outputs, and simulate two patterns and then check the outputs, and simulate a third pattern and then check the output. It will actually do this as a mathematical operation, and it can actually guarantee you a certain amount of correctness. Okay, I hope that could make sense a little bit. I'm not covering assertions in this class. That should be in system verification class, the specialization. But I'm just trying to let you know how things fit in. This is the big picture. Okay. Is that helpful?
Yes.
Okay. If there's any of you that's confused, just let me know. So this is part of the system Verilog features. You can write assertions. Okay. And that's how you do it. And assertion is nothing else but saying that a type of pattern. And there's a lot of flexibility because with assertions, you can say a random number of kind of timing interval between the shifts. Like I want 2 upward transitions, like 0 to 1 transitions, but there could be arbitrary number of time in between, right? So the synthesis to the simulator can actually check for all possible combinations, but it uses a mathematical approach. So it doesn't actually have to do like I generate one bit pattern, then I put it in and simulate, then I check one bit pattern and generate 2 bit, because it's very slow, right? But for now, for this class, you can do that because I want you to think through all possible combinations, because you still need to use this way of thinking in order to generate assertions. You cannot run away from this way of thinking. Okay. All right. So now that we have gone through how do you specify what the system will do, and how do you specify how you will test the system. So how you specify how to test the system, you have to say what type of input patterns I'm going to put in and what is my expected output pattern. You cannot just say, I want to tell you what's the input pattern I need to put in. Then how are you going to test? You don't know what is the expected output. Neither can you just say, I want this output, but you don't specify the inputs, right? Then it's like, what test is this? It's more of like you have to specify the exact sequence of inputs you're going to put in, all the possible combinations you want to test, and what are the anticipated outputs. And I have a third row here where I talk about test case, because that's just kind of like helpful for you to group types of tests lah, because there are types of tests, and then within that each type of test you can kind of randomize, throw different numbers and different conditions, or like different lengths and all that, but you're basically testing for one type of function. Okay, right. The third step now is you've got a specification of what it will do, you've got a specification on how you're going to test it, Now let's talk about how you're actually going to design the circuit. Okay, that's the interesting part. Okay, great. So I'm going to ask you, how are you going to design this circuit to test like whether there's 4 passcodes, right? How are you going to design that? You know, maybe one way you could think about it is maybe I can do a algorithmic flowchart lah. I can just write a flowchart to actually explain how this will go lah. Okay, I can actually say the first thing is I have a choice. Choice is this one. First thing is edit text. This first key equals to 5. Okay. Okay. And I can actually say so I can actually do some kind of flow diagram like this, okay, flow chart like this, and you're all familiar with flow chart. And sorry, this one will be confirm key. Insert. Okay, so for simplicity, down arrow means yes lah, right arrow means no lah. Okay. So I could actually draw a very simple flowchart like this. Okay. And then I would say there's a behavior. Okay, everybody can see this, right? So this is kind of my first very simple attempt. I want to kind of specify lah, like design some kind of algorithm lah, some kind of way how I can implement this lah. So maybe the idea would be I can first check is the first key equals to 5. If it's true, then I go to the second check. Is the second key equals to 6? If it's true, I go to the third key equals to 0. Then if it's true, I go to fourth key equals 6. Then I can say after this is confirm key press. Okay. And at any point, if the answer is no, okay, if at any point the answer is no, it straight away just go into this loop where if the confirm key is not pressed, it just checks is a confirm key pressed, another key pressed. Then if it's confirmed it's pressed, straight away you know that it's unlocked, it goes to 0. So it doesn't really matter whether you're talking about 4 keys, 5 keys, 2 keys, 3 keys. This branch will take care of it. Okay. If it's 5 keys, this branch will actually move up here. Okay, so this flow chart is not perfect. A lot of cases we have not considered. I'm just showing you a partial example, but it's just how do I get started with this design? How do I start thinking about this, right? So one way I can do it is you're kind of familiar with programming, you're kind of familiar with thinking about things in sequential fashion. You can actually do something like this. Okay. And then the question is, if I've got something like this, how do I do any kind of logic? Okay, how do I do any kind of logic? Because there's something that's happening here, right? When you're saying it's a first key press, you're waiting for an event to happen, right? You're waiting for something to happen, right? An event to happen. And if there's no event to happen, you want to maintain the status quo, right? Am I correct? And then here you're waiting for an event to happen. So implicit in this is that there could be a lot of time happening there, and then you're waiting for an event to happen. And if you look at this check, right, you can actually almost think about it as this is one mode. This is the mode where your circuit is waiting for the first key. Okay. And then once you receive the first key, if the first key is equals to 5, you are actually transitioning your circuit into a second mode of operation. Okay, and this second mode of operation is whether it's checking whether the key is going to be 6, right? And then if the key is really 6, it will change mode again to where you are looking for whether the key is equals to 0. So what do I mean by mode? What I mean by mode is if you think about combinational circuits, if you design a combinational circuit, the combinational circuit is just going to do this function. Okay, is the key that is received, is it equals to 5? Is it equals to 5? Is it equals to 5? But why I'm saying mode is because depending on what happened in the past, the logical operation, the combinational logic operation that you will be doing will change. So the mode is actually a way of thinking about selecting a combinational logic operation that will be in effect or in force at that particular moment. Does this sort of make sense to you? So what I can sort of say is that this is one mode because it is doing one type of combinational logic operation. And if this results, I receive this result, and this result can either go here or go here. Going here is a second mode. Going here is another mode. It's a different mode. So what I'm actually saying is that each of these decisions are actually implementing a different operation, which I call it a mode. Later, we will look that mode actually can be thought of as a state of your circuit. Okay, but I want you to think about a mode as basically it's a type of computation that your circuit is doing. And so the way you can actually make this circuit flexible, like I actually want to have different sequence and all that, is because what you're doing is you're effectively changing the mode of operation of your circuit. Okay, right? Okay, let's see what do I mean by that? What do I mean by that? Okay, I'm going to just to ask you to take it on my word that you can actually design a comparator circuit. We're just going to call this a comparator Okay, what I mean comparator is just equals Okay, it's an equals function. Okay, How do you design comparator? Well, you can create the truth table. Okay, you can create the truth table like this, right? So if you can have, let's say, a 2-bit comparator, right? You have A0, A1, B0, B1. Okay, so this is 2 bits, and basically this function is this is the output lah. Output. So you can look at all the possible combinations of these bits. So when A0, A1 equals B0, B1, this is 1, that means they're equal. Otherwise, it's going to be set to 0 lah. So what I'm just showing you is that this is a comparator circuit. You can always write out you can do your Carnot map and you can generate the comparator circuit. Or you can actually just put the equals in Verilog RTL and it will generate the comparator circuit for you. So we are not going to worry ourselves about how to generate the comparator circuit because you know how to generate it already. And we are not designing at that low level. So I'm just going to say that this comparator circuit, there will be 2 inputs here and there will be 1 output. And this output is actually, is it equal? This output, you call it is equal. Okay. So this comparator circuit is one type of circuit. What is it doing? It is looking at the button that you pressed. Okay. So it's looking at some kind of input where you're saying button pressed. And then it's comparing it with, okay, so the first mode is key 5. Lah. Key 5. Okay. Right. It's comparing, is it equal or not? Okay. Do you follow me? Is this, do you find that this is okay? Or you find that this is a problem? Okay, right? So if you look at it like this, it's roughly this is one combinational circuit. And when I say I'm selecting mode, you're like, how does that happen? Yeah, because you know, one combinational circuit is a combinational circuit. You design this, is this compare fixed number of logic gates, right? So it's not going to change. The circuit is not going to change. But you have this case where you have to check whether the first key equals to 5, the second key equals to 6. So one way I could do it is I could actually have second circuit, key equals to 6. A third circuit, key equals to 0. Key equals to 6. Okay. And then I have some way to choose which circuit is in operation. Okay. So you can think about it as maybe I can put an enable pin here. Or better yet, I actually need the result, right? I actually need the result here, right? I'm actually going to be determining the result, right? So I can actually put one nice giant multiplexer. Okay, it's not really a giant multiplexer, it's just a multiplexer. Okay. And the output here, I would say, is the result. Okay. The input here, the selection here is called the mode. Okay. Okay, something like this. Okay. Does this make sense to you, what I just drawn for you? Is it okay? Can you follow what I just drawn for you?
Yes.
Okay, so yes, okay. You probably wouldn't actually design circuits like this, but you can, right? But why am I going through this? Because I want you to understand certain very fundamental concepts. And one concept is this idea that although you are designing combinational circuits, and these combinational circuits has a fixed function, what you're essentially doing in a digital circuit design is you are actually selecting the mode of operation at any one's instance in time. So you can start to see that if I have 4 units of comparators like this, I pretty much can say in the first mode, I'm actually selecting this combinational circuit to perform its operation and give me the output. And based on this output, I will decide what is the next mode. Okay, because I'm not done yet. I just need a fifth mode. So 1, 2, 3, 4. There's a fifth mode here. Compare key, right? The fifth mode here. Confirm. Need a fifth mode here. So what I'm trying to illustrate to you is that this flow diagram, I can actually think about it as having different modes of operation, and that each mode of operation is basically one logic circuit. Okay, in the simplest example here is a comparator on adder, but it can be more complex, right? It's just some inputs process, get some outputs. Okay, and basically I reduced this algorithm to a problem of what are my basic computational tasks, or what is the operation in each mode, how many modes are there, and then I have some method to select which mode is operating as this goes by. So for example, maybe when I start up my circuit, I'll say, okay, I need to enable this mode. Okay, is it key equals 5? So once I enable this mode, and then it says, okay, if the key press, if there's no button press, I remain in this mode. Okay, but once there's a button press, I need to check whether it's equal or not. And if it's equal to 5, I need to shift it to this mode. If it's not equal to 5, I need to shift it to this mode. So if it's equal to 5, I need to shift it to this mode. If it's not equal to 5, I need to shift it to this mode. And that's all controlled by this mode signal. Okay, so you get this concept. So basically you can think about all of circuit design as there are fixed functions, fixed fixed logical operations, and you're kind of choosing between the logical operations. When does it happen? Okay, can or not?
Yeah.
Okay, so the easiest way to actually think about a mode, that's your state. Okay, that's your state. Okay, what is a state? What is a mode? It's nothing else but just a sequence of numbers. That's why I draw it in terms of a multiplexer here, because literally if there are 1, 2, 3, 4, 5 modes, you will need 3 bits. 3 bits can give you up to 8 modes. Okay, so this mode is equivalent to 0, 0, 0. This mode is equal to 0, 0, 1. This mode is equal to 0, 1, 0. This mode is equal to 0, 1, 1. And this mode is equal to 1, 0, 0. Okay, so this mode is actually a 3-bit signal. And this 3-bit signal literally is being stored by 3 flip-flops. I got flip-flop 1, I got flip-flop 2, I got flip-flop 3. So these 3 flip-flops are actually storing your mode. Okay, and I use the word mode because it's generic, but now I'm going to change back. It is actually state. Okay, so these 3 flip-flops are actually holding the state of your circuit. Okay, and this state of your circuit is just saying which operation are you going to be choosing at any one instance. Okay, is that okay? Is that quite clear? So this is nothing new. You know all of this from digital electronics. It's just maybe you haven't realized it from this point of view. So when you're designing a state machine, what you're essentially designing is you're designing the modes of operation of your circuit, and then you will have a computational part of it, and you've got the mode part of it. And then the next question is, okay, this is being held by flip-flops, but how do I know what mode, how to change the mode, right? This is where you will actually use the results from what is my current mode. Okay, so you need to check your current mode. How do I decide what is the next mode to go, right? So I need to know what is my current mode. So when I started, my current mode is mode, so now I'm going to use just integers lah. I think you can understand integers, right? You can understand this just going to be just a digital representation of that, right? So I call this mode 3 and mode 4. This mode 2. Okay, I think I'm just going to make it a little bit simpler. Since we're going to start with this mode here, we're going to start with this mode here. I just call this mode 0 lah. Because on default, when you start up everything, you're going to go to mode 0 lah. So when you press reset, everything resets, automatically this will go to mode 0. So you're rating for mode 0. How do you know to shift to mode 4 or to mode 1? Okay, that's the open question, right? Because we said that from your algorithm here, I start at mode 0. Depending on whether I press the button, whether it's 6 or something else, I will go to the second mode, mode 1, or I will go to mode 4. You follow me with that? So now I just told you that the mode is actually stored by flip-flops. Okay, they're remembering the mode, right? And this is now state, the flip-flop storing your state. State is nothing else but mode, okay? So how do I know how to change modes? Because that's basically what I'm trying to do. I'm trying to change the mode, right? Whether I'm using this computational block or this computational block or this one, right? So I'm starting with this. So how do I know how to change that? Well, the operation is actually, the operation to change the mode, right? But it's actually, if I'm in mode 1, if I'm in mode 0, okay, the condition is, if I'm in mode 0, okay, if is equals 1, then the mode will go to mode 1. If is equals 0, then the mode will go to mode 4. Okay, this is the condition. This is the condition that if I'm in this particular mode, how do I change mode? I change mode if this output signal, because if I'm selecting this mode, this output signal is actually this output signal from this computational block. Okay, so if this output signal, okay, I'll use comparator result lah. Comparator result. If this signal is 1, I need to change the mode to logic 1, to mode 1. If this signal is 0, I need to change the mode to mode 4. Okay, but that's only if it's mode 0. Okay, now if I happen to be in mode 1, then it's different, right? Because if the comparator result is 1, I move to mode 2. If the comparator result is 0, I move to mode 4. Then if I happen to be in mode 2, and so on, this goes to mode 3 and then mode 4, right? So now you start to see that changing the state, changing the mode depends on what input signals. It depends on the current mode as well as some other inputs. In this case, is the results from this. Do you follow me? So sometimes this is sometimes drawn. People will draw this sometimes, and they call it cloud of computational logic. Shortcut way of doing it would be okay. They will literally just draw a cloud here, okay. And then there are two types of input that actually goes in. The inputs are, you call it the present state. Present state is nothing else but these values feedback in and inputs. So there are two types of input of things that go in this combination logic. So this is a cloud of combination logic that will determine the next mode of operation. Okay, whether you stay in this mode or not. Okay, and that will depend on signals that are the mode itself. That means you take these very same signals, you loop them back in, and they go inside some combinational logic here, as well as some input. So the inputs will be, for example, the output from here. So this is the way we talk about it, right? There's always going to be a cloud of computational logic going into flip-flops. That is nothing else but a state machine. Okay, and how do I implement this? Well, if com result equals this one, then mode 1. If you look at this is nothing else but another truth table, right? What is the two inputs? It's a two input truth table, one output. Input 1 is mode, input 2 is com result. Okay, but mode is not 1 bit lah. Mode is 3 bits. So it's 3 bits plus 1 bit is 4 bits. And the output is actually whatever values of mode 1 here lah. So you start to see that, oh wait, this part here, this is a combinational logic with these two inputs. And this is also a combination logic with these two inputs. And this is also a combination logic with these two inputs. And now I look at these things, I actually see 3 combinational logics depending on the mode. Doesn't that look very similar to this? Where if I have a certain mode, I will select this particular truth table or this particular combinational logic. If I have this mode, I have this particular combinational logic. And if I have this mode, I have this particular combination logic. So now you start to see the magic of multiplexers and this mode idea. All of a sudden, state machine design has become really, really easy. It's just a multiplexer. And the input to this multiplexer is basically the mode signal here. So you have your state machine here. Okay, your states are being held by this flip-flop, and you have combinational logic that is saying how to change the mode of operation, the state of operation. And now we've defined it. If you're listing all down carefully, you're defining in terms of, okay, I can select which next state is depending on my current state. Okay. And this state is used to also select which operation on the data. And this is very clean now because I can tell you this path here, calculating and setting the mode and the state, this is called the control path. This path here, where depending on the mode of my circuit, I'm choosing which logical operation to operate on data. This is called the data path. Okay. Now you look at it, you're like, yeah, everything, this is logic gates here, this is logic gates here, 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 this is flip-flop. Yeah, they're all the same, correct? But conceptually, I can actually split up the design to a data path design and a state machine design, which is also the control path. And they're actually kind of similar, right? Because the state is just telling you which mode of operation am I doing at each particular point, okay? And I've also shown you multiple things because I've also shown you that this if operation can effectively be implemented as a multiplexer, right? Because the multiplexer, if operation is just choosing which operation you're doing. So every operation in the if can be its own fixed combinational block, okay? And then you just use the multiplexer, and the if condition is basically the choice here, okay? Right. Tell me how you think about this. Do you understand this? Because I've effectively compressed half of digital electronics. At your undergraduate digital electronics, you probably take like a 12 or 14-week course. Roughly about half of that time is devoted to sequential state machines, or maybe at least 2 to 3 weeks. I've compressed all of that in this 1 hour. This is everything you need to know about designing state machines. Do you follow me? Does this intuition appeal to you? Can you actually just start sketching this out based on algorithm like this? Because I'm showing you a lot of things. I'm showing you now that your state machine is nothing else but a mode setting of what operation you're going to do, right? And you may have heard of something called Mealy machine and Moore machine. Now I'm going to combine all the concepts to you and let you think about it, how to think about it. So basically, I like to draw flip-flops as a black box like that lah. Okay, I'm just going to draw one, but you understand that if this is like a 2 bits are coming out, means there are 2 flip-flops. It's like 64 means there are 64 bits, right? You understand that lah. And I'm going to draw my favorite cloud, like what I like to call the cloud of combinational logic. Cloud combinational logic is nothing else but this part here. It's just combinational logic. Okay, it's implementing some kind of choice and all that. So I'm just going to draw a cloud of combinational logic like this. Insert. It's my cloud. So I'm telling you nothing else but a state machine is actually going to give you the mode of operation here, and you will have a bunch of inputs coming from somewhere, as well as the value of the present state. That means the present mode, going to this. And this is the control path, because the control is actually, the control signal is basically which state, which mode you're operating. And you can think about the data path as some combinational logic again, which you choose, right? Okay, what does this combination logic doing? This combination logic is actually generating your output signals, okay? Generating your output signals based on what is the mode of operation you want it to have. And also be generating the output signal depending on the data you receive from outside. This is the general form of all state machines. Okay, it is the general form of all state machines. When you design a state machine, what you're essentially just designing is you are defining the states of the modes. Then you're defining what is the condition where I can decide the change of mode, and that will depend on the current mode, the current state, as well as some inputs. And then so this part here is the control path, and this part here is the data part, because the data path is actually creating the output. Okay, what is the output? The output is just what kind of operation are you computing based on the mode which you are using. So this mode, this control part here, the mode is actually choosing which operation to use, and this is the data you're operating on. So this cloud here is actually this part of the circuit, and this part of the circuit, the control part, is actually this. So this is the diagram for milli machine. More machine, you just minus this. And some of you are used to, you're saying counter and all that. Well, in a counter, you don't actually have any logic here. It is just this. Okay. Generalized state machines, and I'm fusing a lot of concepts. I'm showing you how this basic combination can design almost all digital circuits. And it's nothing else but saying, I have a bunch of modes which you define. You define in the flowchart like that. Right? A bunch of modes, and each mode has its own operation. It just so happens in this case is equals, but later on this could be plus, this could be minus, right? And now you start seeing that, hey, this looks a lot like a microprocessor, and you would be right. A microprocessor, the instruction is the mode. It is choosing which operation to perform, right? Except that the mode is now programmable. That's a different story, okay? Whereas in state machine, the mode is sort of hard-coded. Okay, so do you understand this big concept? Because with this concept, you can design any circuit already, pretty much any circuit. So take a minute or two, let this sink in a little bit. This is a very important concept. This is the summation of all the design part. Yeah. How is it, everyone? Are you able to follow this?
Doctor, I have a question.
Yes.
The control part, then how do we design the selector for that?
The selector for this, okay.
Yeah.
So again, okay, good. That's a good question. So you check this. I'm listing out what are the conditions to change mode, right? So if mode 0, if comp is out. So now you start to see everything in the if is basically your selector signal, and then the mode is output. So I'm going to take this part here and I'm going to put it in the next slide. I'm going to show you how to elaborate this more into a circuit. And then I'm going to show you how you can easily convert this straight away into combinational logic. You actually don't even need K-maps. Okay, so you look at this like that, right? So we're saying if it's mode 0 and it's comp result. So what I can basically do is I can basically put my input signal here. And this is my selection signal. My selection signal is basically, if I look at here, is mode, right? But sometimes it's not actually dependent on mode alone. It might be if mode plus something else. Then this will be a combinational logic here that is going to the selection. Okay, but for now it's just mode. But what I'm saying is that it could also be you have a combinational logic sitting here, which decides the selection here. That's also possible. But at this moment, because you're only conditioning on mode, okay? Okay, sorry, mode and com result lah. So mode, mode. Okay, sorry. Let me do it one way. There are actually many ways to do it, but let me just show you one way, and then we can talk about the other ways. So, okay, if mode, I can have mode 0, I can have mode 1, and I can have mode 2 here. So that's great. So I can remove this selection signal because I move this to the side. Okay. Now, how do I implement this? Well, that's another comparison, right? And then you will just input and here now you put the binary representation for mode 4. Mode 4 is 0. You put the binary representation for mode 1. Now, is this clear to you what I just did? This is a cloud. What is it doing is implementing mode calculation depending on some input value here. And then it's actually sending it to the mode. So I'm using a 2-stage multiplexer to do that. One multiplexer based on mode and one multiplexer based on com result. I could also have a more complicated logic function here and a single stage of multiplexer. I could do that, but what I'm actually trying to do is I'm trying to actually show you that this recipe, everything can actually be expressed as something like this. And if you express it as something like this, you need not fear combinational logic design, state machine logic design anymore, because you can actually just eyeball it and you can just draw the circuit by hand. No problem. Okay, so this will be mode 2. Now I'm implementing these two parts of here. This is my state machine. Do you follow this?
Yeah, okay.
Okay, yeah, you follow this. And I also like to further tell you, okay, this is another trick. You can basically design circuits of multiplexer completely, right? Because you know that if you have AND, OR, and NOT, you have an AND gate, an OR gate, and NOT gate, you can design any logic, right? Because AND, OR, and NOT forms a complete logic. And NAND and NOR also forms a complete logic. Okay, so how do I show you that? I'm going to show you how to design a NOT gate with a multiplexer, an AND gate with a multiplexer, and an OR gate with a multiplexer. And that tells you that I can design everything, right? Because using one multiplexer, I can design OR, NOT, and NAND gates, OR, NOT, and OR, NOT, and AND gates. So I can design every possible combinational logic using just this. So I can actually put something like this. And I'm just going to say this is in. It's out. And if you remember your NOT gate, stare a little bit. This is a NOT gate. Do you agree with me? Okay, stare at it a bit and tell me you agree with me that that is a NOT gate.
Yeah, that's a lot.
Okay, wonderful.
Yes. Okay.
Let's go for an AND gate. This one. This is an AND gate. Take a look at it and tell me you agree with me.
Yes, Doctor.
Okay, OR gate lah. This is not exactly the correct symbol, but okay lah. You get it lah. This is an OR gate. Okay, so if you agree with me, this is an OR gate. I've effectively shown you that just using multiplexer alone, I can design the entire circuit. Any digital circuit you give me, you just give me a multiplexer alone, I can design any combinational logic for you, right? And that's why I'm confident to just do all of this in terms of a multiplexer. Okay, now stare at this, tell me that you agree with me this is an OR gate.
Hi, Doctor.
Yes.
Just asking. I wouldn't be using like masters to design your circuit be bad. I mean, it's basically pass transistor. Wouldn't the signal get weaker every time?
Ha, okay. One of a VLSI question. Great question. Okay. Short answer to your question is yes, you wouldn't actually be going to this level to specify multiplexers lah. You wouldn't lah. You would actually leave the synthesis tool to do all of this for you. The synthesis tool will find the best solution. The way to think about the pass transistors is there's actually a CMOS version of the Mux gate lah, which is basically a NMOS and then a PMOS in parallel lah. So that one, the signal, well, yeah, you're right. It would be weaker in time because there's going to be voltage drop lah. So you probably wouldn't be using a pass transistor multiplexer, but pass transistors are not the only way to make multiplexer lah. They are the cheapest multiplexer, but you can actually make multiplexers out of stacks of NMOS and CMOS lah. So it's really a choice, but I'm teaching you this because I would like you to learn this way of abstraction, this way of thinking. I want to remove the mental block that most of you, if not all of you, have, that when you talk about combinational logic, you need to do K-maps. I'm effectively showing you today that you can throw your K-maps away, right? Because as long as you can specify the logic in this form, the synthesis tool can convert this into NOR NOT gates or NAND and NOR or majority gates. Let the synthesis tool do it. You don't care about it, right? Because the synthesis tool is optimized to death, okay? But what I'm saying is that you may worry that you don't know how to see this in circuit form. So as long as I show you that there is one possible circuit implementation that you can just sketch out like nobody's business very quickly, you can always rely on a tool to find the equivalent in terms of NOR and NOT gate, or in terms of NAND and NOR, or in terms of majority gates and all that. Do you follow me with that? So what I'm teaching you with multiplexer is I'm just trying to teach you a way of thinking about how to quickly and rapidly design a gate, a circuit, so that you can tell yourself that I'm not worried about K-maps and N and OR and NOT gates yet. And the reason I'm showing you a multiplexer is because after this, I'm going to show you two more steps. One is I'm going to show you that a multiplexer is actually implementing a truth table. And that is goes back to why from the beginning I asked you, you have to focus on the specification, which is basically nothing else but saying the truth table, because at the end of the day, you can always convert the truth table into a multiplexer implementation. And later on, you can rely on the synthesis tools and all these fantastic tools to actually map it into the standard cells or into the hardware. The second reason I want to show you this multiplexer is because I want to show you there's a one-to-one mapping between the multiplexer and your Verilog code. So everything becomes a recipe. I've turned a design process into a McDonald's process. That's where we're going with this. Okay, I don't expect you to actually implement this in multiplexers. That's not the take home, but it's a way of thinking that allows you to very rapidly put logic down and to reason about your logic. Because if I'm talking about it in terms of this circuit and this circuit, you're just choosing this and you're just choosing the modes. This is very easy to think about, very easy to specify. And there's a recipe and you can focus on the specification, which is basically the design of how many modes you have, what are the operations you have per mode. Easy to check. And then you leave the synthesis tool to actually optimize these. It may not actually put a multiplexer here because again, if you have like 20 different modes, this multiplexer is not going to cut it. It's going to be too big. And then you have and then there's another way to do this, it's like, why are you doing it this way, right? I just show you an example of something that could be an easier way to implement this, right? Instead of having this multiplexer, why don't I just put a multiplexer on the input here? Instead of then I'm using the same logic here, the equals logic, but then I'm just choosing different keys. That there are many ways you can implement this, but what is nice about this framework is it allows you to reason about your design and actually just look at it and partition your circuit in terms of like, okay, I know this operation is doing that. And then you leave the tools to do the optimization for you, right? Is that helpful? Is that explanation helpful?
Yeah, yes.
Right, because I want you to develop an intuition around circuits. I want you to just look at, oh, it's a sequential circuit, nothing new, nothing difficult, right? You can actually just kind of like sit down, sketch it out in half an hour, you got a design already, right? Because really, is that straightforward? And I actually want to show you that the actual design process is not creating the digital circuits, it is specifying what are your control states, what are your modes, what are your operations, and what is this sequence that you are implementing. That is the design part, not creating the gates. Okay, and that is where you need to focus. And now that you got this tool, you can focus on that, right? Because again, who says there needs to be this many modes, right? Are you sure I need this many modes? Can I just use 2 modes? Can I use 1 mode? Right? I can actually use 1 mode, I can just say key equals value in shift register. Essentially collapse all of these into 1 mode. Then I just change the shift register. Right? So you can focus on it that way. That's where I'm getting at. That's why I'm teaching you this way of thinking. But for those that are maybe less familiar with design, this will immediately give you the confidence. Yeah, you can design any circuit, right? Because like I said, this multiplexer implementation, you can always convert it to logic, right? You can pay some undergraduate to do it, or better yet, you just put it into a synthesis tool. It will just spit out the logic, right? Okay, so now what I'm going to show you is I'm going to show you that a multiplexer is really implementing a truth table in a very simple way. So I'm just going to call C for this is sorry, this S is for selection pin. And I have A and B here. One input signal, one output signal. Truth table. Multiplexer implements a truth table. If this is a 2-bit signal, that means you have 0, 1, 2, and 3. Okay, so it's like we have 2 and 3. Then you actually have a 2-bit signal here and a 1-bit signal here, right? And then out. Out does not need to be 1 bit. Out can be 4 bits. Now, effectively, I've shown you this multiplexer. And whenever you have a truth table, you can always slap a multiplexer in it. And again, this multiplexer, you can optimize it. Like you can do, arrays of 2-input multiplexers, which are not that great, or you can actually convert it into logic. But yeah, fine. You know that the tool can always do for you. That is not design anymore, because the tool will basically frame this problem as a combinatorial optimization problem. That's where the Boolean logic comes from, and you'll be able to get the optimal setting for you, the optimal configuration based on your library for you. But this is just to show you that as long as you can create this black box mapping, what is the inputs and what is the outputs, multiplexer will be able to do it for you. And now I'll show you the final piece. How do you actually think about this in terms of Verilog code? If this multiplexer is going into a flip-flop, okay, if this multiplexer is going into a flip-flop like this, okay, then the code essentially for this is, okay, I'm using the old Verilog lah. So if you want to use the newer system Verilog, it's possible. Begin, end. So this is a state machine. So I'm just going to call. You have to declare your variables lah properly lah, the registers and all that. That one I leave it to you to figure out. So I call it state. So this will be if s equals 0. This is one way to do it, right? So now you see why it's so clean is because this multiplexer is basically implementing a truth table. I can write this multiplexer in Verilog as an if-else statement, or if it's a multi-input multiplexer, I can also write it as a case statement. Bit you will have 2B00 state. 2B 0, 0, 1. You can have 2B02, 10 state C 2B1. Okay, state C, this is just, you substitute your favorite bit lah. What is the bit you want to put in, or you can even substitute maybe A plus B or something like that, or some other logic function, or A and B or something like that lah. I mean, in general, it could be many things lah. But what I'm just showing you is this is a template. This is a template for how you can write state machines. So once you're able to frame it this way, you straight away can just copy and fill in the blanks. You have this already. It's no problem, right? And if you don't have this state, if you're just talking about an output like that, talking about something like that, nah? Okay, that's easy as well. Combinational logic, I like assign statements. You can say assign out equals, again, s equals 0. So if s equals 0 is true, out is going to be equals to A. If not, it's equals to B. That's it. You're done. That's Verilog in a nutshell. Do you need to know more? No, you don't. That's it. This was synthesized, and you rely on the two-to-two optimization for you. Right? Of course, if you ask me, yeah, if you got many years of design Verilog, there are going to be shortcuts way in writing this, but my goal is to teach you the pedagogy to really get you to understand this on an intuitive level, to lower the barrier to entry. And with this way of thinking, you can design as complicated a circuit as possible. That's why you spend a lot of time defining the specification and defining the test cases, because that makes you think very carefully about what input and output patterns need to happen. And then you figure out either you start with an algorithm, or if you don't want to start the algorithm, you can straight away start the state machine route. How many modes do you have? And then you define the modes. And in this case, you're talking about designing a state transition diagram, right? Which you're all familiar with. Each bubble is a state. Okay. And corresponding to each state, normally there's an output, but you don't actually have to define an output. You can define a function, right? So when you are doing this transition like that, this is the milli machine. Normally they will just put you have given set of inputs, right? Normally each transition, the transition happens on an input, right? So again, the transition of the state, the change of state depends on input, right? But what's implicit is in this state, you are actually conditioning it on the state itself, the mode, the current mode itself that is represented by this bubble, and whatever input is this, then that's going for the next state, right? So this output given an input, this is nothing else but a logic function, right? Because let's say if the output when A equals 1 and B equals 1, then this is nothing but an AND gate, right? Because A equals 0, B equals 0, maybe you get a different output like that, right? So you look at all the output versus inputs for milli machine, that's nothing else but this logic function here. Okay, so I'm showing you several different ways to think about it because they are just slightly different concepts, but they are just getting you to the same point. At the end of the day, there is a control circuitry that is telling you which mode, or in digital electronics term, they call it which state of operation is your circuit in. And within each state, you are doing something in the data path, some kind of combinational logic operation. Because everything you're doing, actually, you're designing combinational logic only, right? You're designing the next state is you're just calculating what will be the next state is. But the reason you're not thought about it this way is because there's so much focus on JK flip-flops and drawing circles on the Carnot map. So you don't really understand what exactly is going on. This is an intuitive way of thinking about it. It is exactly the same as the Carnot maps. Exactly the same, nothing different. I'm not teaching you anything different. You know all this already. It's just a shortcut way to do it. And I like it because I can actually write Verilog code directly. Once I'm framing the problem like this, I can write Verilog code from directly. And all I need is always block with case statement or if statement and assign statement. I can write everything already. Every design you can conceive. Right? How is that? Okay? All right, it might take you, you might have to re-listen to this lecture, this session again to kind of pick up. And if there are any questions, feel free to put it on the WhatsApp group, or you can post on the forum in ULearnX, or we can discuss it in the next session, the discussion. But this is pretty much cramming all of digital design here, and everything beyond this is your creativity and how you can think about all the possible corner cases. That's why there's no other way to teach you design than you have to do design. But once you understand this viewpoint, the design process becomes very straightforward, and you suddenly become very free to focus on the aspects that matter, which is you define how many states are there, and you define what are the independent tasks here. And this is just doing state machine, right? You will get more power when you start to combine state machine with memory, RAM and ROM and all that kind of stuff. And where I'd like to touch in the maybe next 1 or 2 session is I want to actually touch on the programmable digital logic aspect of things, which is this idea that actually your logic gates here doesn't need to be hard-coded, it could be software defined. And that gives you a tremendous amount of flexibility in your circuit, right? And that actually is coming from this idea, yeah, you can just select stuff. It's this idea of multiplexers to select and using lookup tables to kind of define logic. But we'll talk about that in the future. So today, I think there's a lot of things I've covered in kind of a compressed form, but I tried my best to put it in a way that I hope you can understand, because this is sharing insight, is not sharing anything new. You know all this already. You actually do. Okay. I just want to point out again, this resource, the Chu textbook, is fantastic because it's got examples, code, and all that stuff. Okay, let me show you. And I just want to show you a little bit more on where you can find a little bit more on the, if you want to take the algorithmic flow chart approach, if you want to actually take this approach to designing the circuit. Okay, so that there is the state machine approach, right? That is, you draw bubbles, the bubbles are the modes, or you can also do it in terms of this algorithm mode. But actually, they're the same. They lead you to the same kind of concept anyway. Right, so this one here, finite state machines. Okay, this is millimore. You see, this is the state register, mini output logic, more output logic, next state logic. This is the same exactly as what I showed you, this bubble, right? This bubble, this cloud here, that's this one here, the logic. This cloud here, you see this is milli is dependent on the inputs as well as state, more is only dependent on the state. Okay, so this is a state diagram. And so here the distinction is, this is a state diagram, okay, and this is showing you how to conceptually represent state modes, and then the input and output function. This is actually like the data path, this part here, okay. And this is the algorithmic state machine. This is the proper way of doing it, where this is the state, this is the testing condition, and this is the output, right? So one of these you actually have to put three. I was actually abusing the process a little bit because by doing this, but actually this is not the proper way to do it. The proper way to build that is you have to look at it from the ASM block. I'm abusing the process because quite frankly speaking, I don't really care, right? Like this way of framework allows me to just think about it. I don't really need this anymore, but you should, if you feel you like the algorithm way more, ASM, this is the flowchart version. This is the state transition diagram version. They are equivalent. Just use one or whichever makes sense that helps you think about the solution easier, okay? So this is saying that, okay, this is, again, you can see this is a flow chart, right? It's an algorithm. It's like writing software code, except that this is not software code. All of this can be converted into hardware, right? And these are two equivalent models: state transition model, algorithmic state machine model, okay? I don't really want to be labeled because again, these are techniques. At the end of the day, whichever you feel more comfortable you use, you can generate the design. That's okay. I prefer more to give you this intuition. You're thinking about it in terms of selecting modes and selecting logic and multiplexers. I find that to be the easiest to me. All these kind of frameworks, recipes, yeah, they can be helpful, but sometimes they get a bit overly complicated. But here is quite nice because it actually gives you how to define, using this. And then this one is the state transition diagram and the algorithmic state machines, but for data path, right? For a system with data path. So you can see this data path because this is the state, this is the control block is going in, but there's an option of which kind of operation you want to choose. You want to choose the addition, you want to choose the logical shift left by 2, then you can choose which. That's what you see here, the multiplexer approach. I really straight away can see this is just giving me an option, either a fixed value, an addition value, or this value, but this is actually changing the state, right? The control path. So here again, the same thing here. I know that the next state is based on maybe a choice either of these or something else. Okay. Right. At this point, how are you all doing? Are you able to follow? Do you have any questions?
I think it's okay, but I think I need to go through the book more.
Yeah. It's okay.
Yeah.
Like I said, last week and this week's lesson is kind of compressed. It's kind of a review of digital electronics, but with insight lah. I'm giving you insight from many years about thinking about this and teaching about this lah. Okay, so if you can pick this up, you'll be great. It's just basically nothing else as a recipe to design circuits lah. And I actually hope you will apply it lah. So I have thought about what assignment I want to give you. So there's that problem-based assignment, the SD-RAM, that one you need to do lah. But I said there were going to be at most 2 other assignments that will help you. I think one of them is I want you to design, you do the specification, you do the verification plan, you do the hardware design for this safety lock system. So you go ahead and just implement for this safety lock system for all the conditions we say, and again with the reset and all that kind of stuff. Give it a shot. That's assignment 1 for you guys. Okay. And the reason is this, because we've gone through some of the discussion on it already. I just want you to finish it up so you get some hands-on, and it's really more of trying to give you just some almost free marks. It's not free marks, you have to work for it, but almost free marks because you've gone through most of it. Now you just have to work through the details to actually do the design. Now there's just one more distinction I want to say lah. Algorithmic state machine, state transition diagram. This is a model of the hardware which you will design. It's not yet the hardware, it's just a model, right? Why? Because this is the design proper. The state transition diagram or the algorithm state machine, this is the proper design. Why? Because it is one way to implement your specification. I can implement your specification with a totally different ASM. I can implement a specification with sort of different state transitions. That's why this is called a hardware model, because it's modeling the hardware. So once you're able to design the hardware model, which is basically coming up with a state transition diagram or with the algorithmic state machine, you can then convert that into hardware. But I've tried to build this intuition. I invert the process a bit. I try to actually just kind of directly, well, not really lah. I started with this algorithmic state machine first, right? And then I just draw the hardware out for you. But I hope you can now see that this is a hardware model. And once you got this model, it's quite straightforward for you to translate it into a circuit. Okay. And again, the idea I'm trying to say is nobody does the optimization of the logic gates anymore because the software is so good. You got free synthesis software. You don't need to do it. You snap your fingers, 1, 2, 3, the computer has already got the logic for you, optimized. Right? So there's no point for you to even go in and try to do Kano maps anymore. And then, like I said, you can't do Kano maps beyond 6 inputs. You just can't, right? Unless you are one of those very special people that can see 4, 5, or 6 dimensions. But even then, you are limited lah. At some point, you're going to run out of inputs, right? Whereas in this multiplexer approach, I can have even 12-bit control signal, no problem. Why? Because I can either consider each multiplexer 1-bit selector, or I can group them to be a bunch of bits, right? If it's 12 bits, then there's to the power of 12 options, no problem. As large number of combinations, you can bring it on, right? Easy to reason about that. That's why I like the multiplexer approach, because it is easy to reason about it, and you can actually think about it very clearly, like, okay, I'm just going to enable this control path. I'm just going to enable that control path, right? And the philosophy here is, again, the optimization tools are perfect at giving you the optimum logic. But what is most important is the algorithm, the model of the hardware. How many states? What computational things are you going to do? Once you define that, your computational tools, your synthesis tool can give you the optimum hardware, no problem, right? But the challenge is, did you get the right number of states? Is there an easier way to do this? And like I said, sometimes there's some cases where you actually can have nested state machines, You can have one state machine running, and within one state, you can have another state machine running within one state. So it's sort of like a mode with sub-modes in it, right? So you can actually have nested state machines. And that's a very powerful tool that I use. So one example would be how you implement timers, right? You want to go to a state where it's maybe incorrect, right? But while you're in that state, you can have another state machine, which is a counter, which is actually doing the timer function. So that's how we would implement the timeout function. You will have a second state machine that triggers or kicks off when you're within one of the states. Does that make sense?
Yes.
Okay. Right. Should I just stop here or can I push ahead and introduce one more concept?
Canada.
Can, huh? Okay. Last concept of lookup tables. Just to sink it in lah. This is our favorite truth table, which is nothing else but a specification of logic. Okay. What you actually see when you see this truth table, now you must not think Kano maps. Now you must think when you see this truth table is basically some black box circuit. Okay. And you're just specifying the inputs and outputs to that black box circuit. Okay. That's what you must see. Okay. So this is, I would say, and you can have some inputs and some outputs. And now these are no longer single bits. We know that all of these can be multi-bit signals, multi-bit input, multi-bit output. Okay. I'm going to show you something a little bit magic. To make it simple, let's call it the ROM. Okay. Are these two the same? Okay, you look at this, look at this. Are they the same? What do you think? What I'm effectively asking you is, can I implement this truth table using a ROM? What do you think? Okay, it's very late. I'll give you the short answer. The short answer is yes, right? What is a ROM? A ROM is a series of boxes lah. Each box you can store a value. So what happens if I store it something like this, right? And each box has an address lah. So I like to think about ROM like post boxes, right? I have a name on the post box and that corresponds to the address. Okay, so address 00, I'm storing the value A. Address 01, I'm storing the value B. Address 10, I'm storing the value C. Address 11, I'm storing the value D. Okay. What is this? This is the truth table. So I'm effectively showing you I can implement any digital logic, combinational logic, using a ROM. All I do is I just load the truth table into the memory, the ROM. I'm done. And does it need to be ROM? No, it can be RAM, and RAM is read-writable, is erasable. That means I can actually modify the logic in runtime. Okay, and this is the magic, right? That's why when you focus too much on logic gates and K-maps, you miss all of this. The real key concept is the truth table, the specification of input and output. Because we can implement the truth table as a multiplexer. I've just shown you that. And that lends itself very nice to very lot code. And we can implement the truth table as a ROM. And the nice thing about a truth table as a ROM is all input combinations have the same delay, propagation delay to get the output. And you know that's not the case for AND, OR, and NOT gates. When you have different logic function, you get this crazy situation where certain logic will be faster to compute, certain logic will be slower to compute, and then you run into troubles with max delay and mean delay. Using a ROM, it's just the access time of the ROM only for all this uniform access time. So using a ROM is a beautiful idea to implement logic functions. And this is a very old trick in microprocessor. In microprocessor, this is called microcode. Microcode is basically I'm implementing these logic functions in a ROM. That means this addition, this equals operation, I'm not implementing it in AND or NOT gates. I'm just getting a ROM, filling up the truth table result there, and hey presto, that's my logic. It's called microcode because then my states, okay, remember I told you the state is the mode, right? And the mode is the instruction in your microprocessor. The instruction will actually choose which logic there will be. And the nice thing about microcode is I can change it without changing the hardware. So I'm now showing you third way of implementing combinational logic. Why? Because at the end of the day, we discovered that everything is combinational logic anyway. The only thing that the flip-flops do is they remember the state for a particular point, and then the next clock cycle, they refresh the mode, the state, either the same state or different state. Everything else, whether you're calculating what is the next state you're going to go, what is the next mode, or whether you're calculating in that mode what computation do, everything is combinational logic. So at the end of the day, digital design, you are just designing combinational logic. That's it. And what is combinational logic? Specifying the truth table. That's it. Really, gentlemen and ladies, that's it. And you can do it with ROM, you can do it with multiplexers, or you can do it with logic gates. Okay. And the nice thing about ROM is programmability. And here's where we start introducing the concept of programmable logic. You can use the ROM to program the logic itself. That means pretty much, let's say, for example, I'm one computational path, right? One computational block. I can program this as an adder, right? So I can use the ROM to do that. Or I can produce this as an equal sign, I can use the ROM to do that. But again, this is a little bit challenging because if 64-bit here, 64-bit here, you've got to the power 128 possible combinations. So you need to the power 128 size ROM for the adder, and that's not great lah. So you may not possibly not use the ROM for that lah, right? It may take too long, things like that. Okay, so certain logic you can implement with the ROM. Okay. And because it's ROM or it's actually memory, you can actually implement this with RAM as well, as static RAM, for instance, and that's known as microcode. That is the idea that you're implementing logic in memory. So this allows you to actually program. So you can actually have this configurable block where the logic itself can be reprogrammed just by setting the content of the memory. And another paradigm in the FPGAs is you can program the connections to this block. Okay, that one will be more, right? So there are two paradigms for programming. Okay, sorry, there are three paradigms for programming. One is the programmable logic. One is you can actually just change the code in memory. There's nothing else but just changing the digital values in this one. So you can implement different truth tables, and that's changing the logic function here. You have a switch where you can choose which inputs are connected to which output. And the third mode of programmability is you have defined some generic modes. Okay, there are different modes with different operation. And then you read the sequence of modes from a memory. Okay, that's nothing else but the microprocessor model. So a microprocessor is a very flexible state machine. Why? Because again, what is a state machine is nothing else but telling you what is the sequence of mode that I'm going to operate. What is a program? A program is nothing else but you are doing a sequence of modes which are actually operating on your data. So the instruction memory of your microprocessor is actually storing the state transition diagram. All right. Okay. So with that, now you know the secret of how to really make really complex designs lah. You can have programmable and all that. We can talk about the programmable thing a little bit more in the future lah. But I think for today, it will be fantastic if A, as a matter of review, you know that you have to start a design, not with design, but with specification. What is the inputs? What is the outputs? What is the name of the inputs? What do the values mean? What does the logic 1 on this input mean? What does the logic 1 on this output mean? What is the encoding you're using? What is the sequence of inputs that you will consider and you will accept? And what is the sequence of outputs in response to that inputs? And what are the sequence of unintended inputs? And how will the output behavior be? Okay, that's specifying your system. That's not design. That's just saying how your system will work. Then you have to specify how you test the system. What actual values are going to fit the system? And what are the outputs that you expect? The sequence of outputs. That means the time components is important as well. It's not just the value, but the sequence, the time, right? After you do that, then you start the process of actually designing your hardware lah. You start with the hardware model, right? Whether you use an algorithm state machine or you use a state transition diagram, it's equivalent, right? And once you got either this or this, you can generate this quite easily. When you generate this, right, or something like this, it's quite straightforward to map it into Verilog. Okay, doesn't matter. You can also go straight to write Verilog, but I actually am encouraging you to start thinking about it in this way, because those people who, there are some students in the past, when they go straight to Verilog, they write Verilog the way they would write C or C++ code. You know, they use a lot of for and if loops, but it's very nice. They get the actual signals, but you don't really know how it actually converts to hardware, right? So with this kind of model here, you know exactly what the hardware will look like in terms of multiplexers, and then it could just be reframed in terms of AND, OR, and NOT gates, right? So there's no confusion, right? It's a bit difficult to actually envision glitches and all that kind of stuff. I mean, they may happen because of AND, OR, NOT gates, but you know, in terms of multiplexer, the logic is straightforward. Okay, it is quite clear, and you won't miss in this case, you actually won't miss like hidden states and all that, right? Because you can easily look at the diagram like this. You can say, oh, okay, my mode has like 3 bits, so that means there's 7 combinations. I only listed 5 here, right? So there are another 2 modes that are undefined. Oh, I better define them, because otherwise the circuit may get stuck in those modes. So it's very easy, very clear. You straight away can see what are your unused modes, unused situations, and then you just make sure you set all of them. Whereas if you start doing like in this fancy state transition and then doing the K-maps, you will miss these kind of conditions sometimes. Okay, so after you've got, so it's good if you can start thinking about it in this form and how to connect this to this and this to this. Okay, and once you got it in this form, or you got it into this form, you're done. That's your circuit, and then you simulate based on this, you verify based on this. Okay, and that's why I said for those who are allergic to programming, you don't like this, you can still do the design, because you'll be giving me a design like this. It's probably going to be a bigger design. You're going to need a lot of paper to sketch it, but that's okay. You can do it. It's not difficult. And the best thing is you can also kind of just draw a black box here, tell me it's a ROM, and then you give me the truth table of the ROM. That works as well. Choose which you like best. But ideally, preferably, you'll be able to give me the Verilog code lah, because you can do more with the Verilog code. You can actually run simulations on it to actually test, and you can write assertions on it later and all that. Okay. All right. I'm pretty much covered what I want to cover today, and as I shared, this pretty much covers all of hardware design. You can do everything now, right now, right? So you can finish all the assignments, everything. What we will probably do in the coming 1 to 2 weeks, I just try to give you a bit more of advanced concepts of programmable logic, how to actually kind of design circuits with memory elements, right? Yeah, right. Because the way to think about it is, sometimes you can use memory to retrieve data, and sometimes memory is just a flexible way of choosing modes or mode sequences. So that's just a framework for you to think about using memory in design. With this design, as you can see, there's no memory here. You're not using any kind of SRAM or DRAM here, right? But more complicated designs, you can do that. And that's just providing you flexibility. Memory is just providing you flexibility. Ultimately, it's a kind of programmability. Right, programmability is nothing else but just flexible, right? I can change the function of my circuit. That's what it's doing. That's why you call it programmable, because it's just, you can change the function. If you just do it in terms of fixed and or and not gates, you cannot change the function of the circuit. Okay, that's where the programmability is interesting. And yeah, so if I can cover the programmability aspect, maybe if we are free, I can also chit chat a little bit about advanced concepts, parallelism and pipelining. These are two of the most powerful advanced tools in digital circuit design. Yeah, but I don't expect you to use all these advanced concepts. I only expect you to use up to this point. The rest are just more a matter of exposure, and if you decide to use it, okay lah. Or we could use the further discussion sessions in the future to talk about specific circuit designs, or like you have some problem with the homework assignment or in the problem-based assignment, you cannot get past a certain concept or implementation, then we can talk about it. Okay. All right. It's probably been a long night for all of you, also for me. Maybe around the table, any final questions before we end the session? Okay, it's getting a little late, and normally after this session, roughly around now, I get a bit worried because either one option is you all are understanding it like 60-70%. You probably need to think about it, try it out, and let the idea in your head kind of seep in, which is good. Option two is you just totally didn't understand what I said, and that's not good. You should let me know in that case. And option, well, yeah, there's kind of just two options lah. So I'm always kind of worried which option is it for you lah. So maybe it's a bit late. Probably not expecting any bright questions at this point. Think about this. If you need me to repeat any part of this in the next session, which should be next Friday, let me know. If you have difficulty with any of the concepts, let me know. But do think about this, do revisit this video. We can talk about this again. I'm squeezing a lot of concepts today, so it probably will come as a bit of a surprise to many of you, but it's okay. We try to make the best use of the time. So you know now that you've learned the major part of it already. The rest is just putting it into practice. Okay. Speaking about the coursework, do we have any tests? Wait, let me check. What was the? Okay, is it? Do we have any tests in upcoming weeks? No, I think I like to repeat lah. I know it just seems like many of you are very busy this semester, and I had promised some of you that I would not make this course too difficult lah. So I'm only thinking that the major project is this problem-based learning project where you have to design the interface to the SD-RAM lah. Okay. Which is you're designing a state machine, implementing an FPGA. This is the major one. Either it's going to be so as I told is because we are in extended assignment, your extended assignment is only worth 40% of the total grade. Coursework mark is 60%. If it's final exam, it's 50 and 50. But we've been running on COVID mode for almost 2 years, so it's 60-40. So out of the 60% of your coursework, I'm thinking either 40 or 30% should go into this problem-based learning project, and the remaining marks will split into two assignments, two design assignments lah. One design assignment I'm giving you today already, which is go ahead and finish this passcode system, implementing all these conditions and more. Just do a nice design, thorough. Start with the system specification, start with the verification plan, and then all the way to the hardware model, because this is not a complete hardware model. We've not considered the case of reset or timer function, or when there are 5 successive errors. We've not even considered the case where There could be the buttons could be pressed at different times. There could be a long delay in that. So all those things you have to design the hardware model for that. Nah. And we've not even considered the case where you might want to change the passcode. You might have your hardware be more flexible. And here's where memory will be very nice. Lah. You can actually just program the change passcode in the memory. Lah. Okay. So I would say that's assignment 1. There's probably going to be one more assignment, and then you focus on your problem-based learning. In fact, you can actually start your problem-based learning now already. Don't have to wait, right? Because I've got the section here on FPGA and on SD-RAM, right? And if you have any questions on this, you can ask me. Some slides, some papers for you to just kind of improve your background on this. Okay, so is just going to be 3 work packages for all of you. You can work in teams. I don't really like the team to be too big because sometimes the learning doesn't happen. I'll say maybe a team of 2 is okay, but just like in VLSI, if you want to have a larger group that is like chatting and discussing things together, you're welcome to do that. But submission, you should probably aim to do your own, maybe at most in teams of 2. Okay, so 3 in total. The major one is the FPGA SD-RAM design, which you can start already. Then you have the passcode circuit, which we have talked about these 2 sessions. You can also start and finish up that design, do a nice one. And there will probably be one more design example, design thing that I will ask you to do. Most likely it might be an I2C controller or something like that. Just to give you this idea of processing sequence in the communication, or I don't know, let's see how it goes. Maybe if you can make some progress or give me some feedback the next week or 2, then I can think about should I give you what should I give you as the second assignment. Is that okay? Does that answer the question?
Yes, Doctor. Thank you.
Okay, Chia Hong, did you get most of it, or which part did you sort of think you might have missed? Not exactly sure what you could hear and what you could not hear.
I think it's okay in general. Just the later part will need some time to digest.
Sure.
We watch
sure.
the video again.
Yeah, watch the video again. Try to watch this video again and maybe 2 or 3 times. And like I offer, if you need, I can repeat parts of this next week as well. Okay, but try to digest it, and WhatsApp is always there. I've been a bit more slow this semester to respond, but I try to respond within the week. So Iz is doing a good job. I don't really answer, then bug me again. Yeah, so sorry about that. Sorry about the glitches. At the moment, I'm putting classes to be every Friday at 9:30. I think I won't ask to shift anything. I'll just put every Friday at 9:30. So on a weekly basis, we just go, do you guys have anything? So, after probably another 2 or 3 more sessions, we actually don't need to have any more classes. I don't really want to overburden you, but the option remains if you want to discuss the specific implementation, ideas, circuit, these kind of things. We have that option. So I just retain that weekly class time, but we can just very quickly check with each other, like on Thursday or even on Friday, to see if all of you need the class or not. But maybe I'll probably have another class next week, maybe another 1 more class the week after, and then after that it will become optional, right? Okay.
Okay.
Okay, so final call for questions. If not, we can end very late already.
Yeah, just last one. So regarding the assignment, so we don't have to implement any more additional specs, right? We just have to follow what is already written in the
no, Gabriel. I actually just want you to
Oh.
implement a complete passcode. So if you miss something, you go ahead and add the specs, right? Because it's just basically I'm saying you have to implement this thing, right? How would you do it?
Okay, sure.
Yeah.
All
So yeah, you have flexibility to do lots of stuff but why I'm giving the passcode thing is because it's maybe for some people who are less familiar with your first time. So since you've discussed part of it, it wouldn't be so daunting, and it's more important you use this as a chance for you to really put in place your design process lah. Like you make sure you know how to completely specify a design. And sometimes you want to have a template. You know you're going to have this kind of table, this kind of diagram, right? Then in the future assignment or the future problem solving, or even for the extended assignment, the final exam, you can reuse lah the template. You just change the entries only, right? And that becomes like a tool for you in the future when you're doing design. You know that you need all these parts lah. And you should also reference the grading rubric here, because this is really how I will be grading your design lah. I'll be looking at it. Like if you make small logic error at this level, I'm not going to penalize you lah. I'm probably looking more for let me just get the rubric out. So many. I'm probably looking more for these conditions lah, like the design specification, as long as you got most of it clear and good. So if you get good, this is like 80% out of 100. So 80 is actually an A minus lah. So if you get somewhere between good to excellent, that's already an A lah. Okay, it's like 4.25 is basically an A already. Yeah, 4.25 is basically an A. 3 is kind of the cutoff lah. If you score below 60, you are probably in danger of going into what's the term? Going into probation lah, academic probation lah. Because although you will pass the course, if you score 60 marks for, you score 59 marks for all your courses that semester, if you were to score consistently 59 marks for all your courses, you will pass all the courses, but you will not graduate your masters, because UTP requirement is you must score a B and above for CGPA, cumulative grade point average, then you can earn the masters. So that would actually mean roughly each course you need to score 60 marks and above, everything. Okay, so the cutoff is actually like 3 lah. Like this is passing mark, if you will lah. Not strictly passing, like if you get 4, you still pass, but you are in danger of not getting your masters lah if you're consistent about that lah. Okay, I hope that helps. So combination of what I told you, and then you just check some of the words here. That's how I'm actually going to be grading you lah along these dimensions of your design and your plan. Okay, right. Final questions. Okay, if none, then thanks for your attention and participation. Wish you a good weekend and good rest, and take care, everyone. Keep in touch. Maybe we see each other next week.
Thank you, Doctor. Thanks, Doctor.
Okay.
Thank you, Doctor, and thanks everyone.
Thank you,
Thank you.
Thanks.
Bye bye.
Bye bye. Take care.
Thanks, Doctor.